So in the last class, we were looking at how we would represent integers using binary numbers. And that was straightforward enough. But when it came to representing negative numbers, negative integers, it got a bit trickier. And so one system was the sign plus magnitude, where you have one bit reserved for the sign. So that was easy to understand, easy to implement. One of the problems with it was that you had two representations of 0. So there's two ways to represent 0, which was not ideal. And I said that's not very useful, and I'll show you now what I mean by that. Okay? So 1's complement then is another way of representing binary numbers that can represent also negative integers. And this is a bit more sophisticated and is slightly better. Okay? So the 1's complement of a binary number is obtained by flipping all the bits. So if you have 0, 0, 1, 0, 1, 1, 0, 1, what's that? It's 5, what's that? Someone do that for me in their head. Well, we've got 1 plus 1 plus 4 plus 8 plus 32. So what is it? Okay, so minus 29 then, if that's what it is achieved just by flipping all the bits. Okay? And that is again easy to understand, easy to implement. It's a bit more useful than sign plus magnitude, and I'll show you what I mean by that. It still has two zeros actually. Like 0, 0, 0, 0, 0 is 0, and all the ones is 0 as well, which is a bit of a problem, but not a big deal. What do I mean by more useful? Well, if you have positive and negative integers stored using 1's complement, you can add them together like you would do for normal binary addition, and the answer is half decent. So here, for example, we have the top number there is 3, okay? And the number underneath, well, if it was 0, 0, 1, 0, 0, that is 4, isn't it? So 1, 1, 0, 1, 1 is minus 4. Okay? So here we're adding 3 and minus 4 together. And you can't do that with sign plus magnitude. But here we can actually add the binary representations and the answer will come out. Now, one of the problems is that when you do the addition, if there's 1 left over, you see that we do 1 plus 1 is 0, carry 1. That 1 that you carry over has to be fed back in at the other end. So it has to come back in there. So then that becomes 0, 0, 1, 1, 1. Okay, which is, in this case we have, look at a separate example. We have again, this is what, 3, this is 11 plus minus 4. And the answer comes back with 7, which is correct. Now that wrapping around a bit there, that's an extra complication. That's unfortunate. But you could see how this is vastly superior to just sign plus magnitude, because you can actually do addition on it and it'll work. You can also do subtraction, but you have to borrow a bit. You know, if you're doing the reverse, but we won't go into that. Okay? So 1's complement allows positive and negative integers to be added together simply enough. Okay? 2's complement is a variant on that. we're not entirely happy with the 1's complement because that wrapped around bit is a pain. And also you still have two representations of 0, which is a problem. So 2's complement is the 1's complement with 1 added to it. So here we have a number up top. That's a positive integer. To get the negative equivalent of that, we flip all the bits and then add 1 to the least significant bit. And the advantage of this is that then things can be added together more simply. So here we have 3 plus well, is that minus 4? What would 4 be? 4 would be just 1, 0, 0, wouldn't it? Yeah. So 1, 0, 0, if you flip all the bits, would be a bunch of 1s and a 0, 1, 1. Yeah? If you add 1 to that, then I'm going to get, that's going to be 0 carry 1, that's going to be 0 carry 1, that's going to be 1. And you'll get 1, 1, 1, 0, 0. So 1, 1, 1, 0, 0 is the 2's complement representation from minus 4. You see here, when we add these two binary numbers together, you can just do a simple add and you get the right answer. The answer comes back, that's correct. So you don't have to do the carry. So that's a big advantage. So that plus 1 there, you just ignore that carried bit. So that means then that if you have logic set up for adding binary numbers, and it only works for positive binary numbers, well, if you're using the 2's complement to represent the negative numbers, then all that logic will still work. You just need to know that you're using 2's complement and that the answer that comes out the end should be interpreted as a possibly negative number in 2's complement form. So I would say it's vastly superior from that point of view. So 2's complement allows numbers to be added simply, and there's only one way to represent 0 as well, which is all the zeros. No. Another scheme you can use is not terribly sophisticated at all, but it does allow you to have any range of integers that you want. So if you have 8 bits, for example, you can go from 0 to 255 if you're just doing positive numbers. If you're using 2's complement and you've got 8 bits, you can go from minus 127 to plus 127, except I'm out by 1 there. It might be minus 128 to a plus 127, or the other way. We could think hard about it and figure out which. But that's pretty much all you can do. You have to have that balance, the same amount above and below 0. Right? But suppose you wanted to have an arbitrary range, like with say 4 bits, you can have 16 possible values. So you could go from 0 to 15. But suppose you wanted to go from minus 2 to 13. That's not so easily done. So we can use a system called offset binary, or XSK. I don't know where that name came from. And the idea there is just that, well, the lowest number in your scheme is 0, and then you just go up from there. So in this scheme, we can only represent 8 possible different things. That's a given. We can only do that with 3 bits. There's nothing we can do about the number of possible things we can represent. But what they represent here then varies. So here we're going from minus 3 to plus 4. If we wanted to go, we could go from minus 13 to minus 6. doesn't really matter. So whatever range of possible values we wanted, we can just use that. So that's a particularly unsophisticated scheme, but there might be a scenario where you want that. So like if you have a particular number of bits on a thermometer and you're going to use it in Ireland, you wouldn't bother wasting bits on -10 and -9 and -8. Do you know what I mean? If it was going to be in Poland or in Finland, you might well go down to -10, I don't know. But you wouldn't waste bits on that in Ireland. So you'd have a different range. Okay? Representing real numbers then is much more complicated. You don't simply have an integer with a decimal point in it. You know, that's a very unsophisticated way of doing that. So the main way we represent real numbers is using a format called IEEE floating point, which I'm not going to go into. But that's what we use to represent numbers, if they're real numbers. So if you wanted to represent pi to very many decimal places, you'd use IEEE floating point. And it can be used for, you know, arbitrarily small and large numbers. It's very closely related to scientific notation that you might have done in school in maths or in physics. But you represent the first part of the number as, you know, a decimal, just a one, you know, with one integer, or one whole number plus the decimal part, and then you have so many, you know, to the power of 10 so many times. Okay, so you can look that up, but we're not going to go into that.